So this is lecture 3 of operations, why they have different lines at a bank than they do at a supermarket. So in a bank, you have one line that feeds into next available teller. In a supermarket, you choose a line. Why do you think those lines are very different? And which line do you think is better? And what do we mean by better? This is operations research. We apply math to anything we can. What's a big difference between a bank and a supermarket? Carts, right? Usually you don't have the giant cart of drug money or something like that that you're depositing, right? Okay, other than Nathan, who, most people do not go with giant carts of money. You have smaller amounts. So you don't need as much space as you do. And so you can see physically the way it's set up at a supermarket, it's filling a different need. So why do you think banks choose to have one line that feeds into next available teller? Sometimes they do these things for privacy so that no one is too close. They do that a lot of times if you're at a pharmacy in terms of picking things up. But what's the advantage of having one line feeding into 4 tellers? Anybody ever see When Harry Met Sally? Oh my God, no one has seen When Harry Met Sally? Not one person has seen this movie. They talk about high maintenance people. You could have somebody who could knock out a line with an extremely long, complicated order. The average wait time, do you think it really matters the average wait time? If you have one line feeding into 4 tellers or 4 lines feeding into 4 tellers? Do you think the average time that people wait is going to be the same? Yeah, the average should be the same. What's going to differ is the variance in your wait. You could have a lot of people who have very fast times, and you could have a very small number of people who have a very long wait because they get stuck behind somebody who has a huge time-consuming need. And so the reason the lines are designed as they are at banks is because this way, if you have that person, they don't knock out an entire line and give a bad experience to a whole class of people. They just knock out that teller, and then everybody else uses those 3 until this person is gone. And so there's a huge subject called queuing theory as to how do you want to manage lines. And what are you trying to minimize? It's much better to make a couple of people a little bit, to decrease their happiness a little bit than to have a small number of people extremely unhappy. And so by doing this, you can do a great job of cutting down the variance of wait time. It's also really bad if you see everybody else being served quickly and you're stuck in that line that's not moving. When you look at Easy Pass and stuff like that, when you're driving through highways, how do we do lanes? You may not have seen When Harry Met Sally, but I've got to assume somebody here has driven a car with an Easy Pass, fast lane, whatever, something. You have about 2, maybe 3 lanes in the highway, and then it spreads out to maybe 5 or 6 if you're lucky. And then you can choose a little bit of which one you want to go into. It's similar to the supermarket where you have the cart that's not so easy to be moving around. And so they try to split it up. And also, for the most part, the transaction is pretty standard when you're driving through Easy Pass. You're not asking for something special when you're going through. So you really know how long each thing is going to take. And really, the length of time you wait is proportional to the number of cars in front of you. The big question is always if you see this huge school bus or tractor trailer in front of you, do you think they're going to be fast and take up a huge number of spaces and move quickly, and do you want to go behind them, or do you want to go to one of the lines that have more cars? But you really want to think about how people are managing lines, managing expectations. All right, so what I want to do today is I want to go back to the Gale-Shapley algorithm. So we stated it before. I want to prove why it works. I'm not going to go into the other part of the article where they talk about assigning students to colleges. I want to just do enough of these subjects so that if you're interested, you can read the rest of the article. And if you're ever in the situation in life where you need to do this, you know what to do, you know what's out there, you know what techniques exist. And then after that, we'll shift to the rental harmony paper. How many of you are planning on going into industry and having an apartment that you will rent with friends? Got to find something you guys are doing. So how do you decide who pays how much rent? Even split. One might hope, but all rooms aren't equal. This room might have the sunlight. This room might be a little bit bigger, right? How do you take that into account? Not surprisingly, we can use mathematics. Now, if you're living with somebody who's not a mathematician, they could be, no, I won't say that. Exactly. But you have to make them think that they're getting a deal. Oh, you're getting the room that's closer to the kitchen. You're so lucky. So you have to find some way to sell it. Okay. So we were trying to match n men with n women. We have a complete list of preferences. And we had no ties. All right. This was extremely important. So while a woman is unmatched, so first, all men who are unmatched propose to top candidate. She rejects all. So that all men who are unmatched propose to the top candidate, to their top. Right. And it could be somebody who's already matched.
No, I agree with this, right? But I'm curious why the woman is unmatched.
Well,
Why the man is unmatched?
Well, as long as there's a woman who is not matched, it has to be a man who's not matched, right? Trying to balance, doing things from the point of view of the men and the women. And so as long as there's a woman who's unmatched, the game is going to continue. Or the courtship. So she rejects all but best, whom she maybes. Now what do we do? Lather, rinse, repeat. So it's a really simple algorithm to implement. The question is, what kind of configuration will this generate? How long will it take to reach that? Will this terminate? So how would we analyze this? Yes?
I mean, first we can look at the role of any women.
Okay.
And say that at any point, the woman's rank of the man she's matched with can only go up.
Okay, good. So let's do some observations. So one is, as time increases for each woman, rank of match can only go up. Anybody remember the special buzzword for this? We used this when we did the virus problem. Mono something, yes. We've got to be very careful because when we're talking about matchings, really just leaving it at mono is not so good. Monovariant. It varies in only one direction. So from the point of view of the women, as time passes, they never do worse than what they currently have. What about from the point of view of the men? Yes. This is a... Well, but you got to be careful because if a man is unmatched, so technically they start off with nothing, then when at some point they get matched. But then if they get matched to another woman, is that woman as good as the woman they had before?
No.
Why not?
Don't they propose to the top candidate first?
So they propose to their top candidate.
At any time, if they're matched to their top possible candidate.
They're always matched to their top possible candidate. So imagine that I should have bought my daughter's Barbies and my Star Trek figures. So, imagine Data proposes to Math Barbie. And Math Barbie says yes. And then later, Math Barbie dumps Data for Lore. And it's his brother, which is really annoying. Is it possible that Data could get back with Math Barbie later? No, because Math Barbie has lore. Math Barbie can never go back to somebody that she thinks is worse than that. So she would never go back. So once a woman dumps you, you cannot come back to her. Right? So what can we conclude about the men? As time passes, no man has a match that improves. Over an earlier match. Right? Because if there was a woman that you thought of higher, you would have proposed to her earlier. And she could have accepted you. So because she hasn't accepted you, you're not going to improve. So the men is also a monoinvariant. A monovariant. There is one little complication with the men, is you could be matched and then you could be kicked out. So you could go from being matched to being unmatched. Whereas the woman, once somebody proposes to a woman, she's always going to have someone. All right, but now we want to show that this algorithm will actually terminate. Can anybody give me maybe a bound on how many iterations it will take? N. Why N?
The man will have no one left to propose to after he's proposed to all his choices.
So man would have no one to propose to after he proposes to all of his choices. And you eventually, I like it, I'm not quite sure that's the phrasing I would like to use.
We could just assume that all men have the same ranking, and then since they all propose to the first woman, and then these n-1 gets rejected.
Right. So my question is, can we create a monovariant attached to this problem? What quantity should I be looking at? The number of matches. So study the number of matches. Can this quantity ever go down as we keep running the algorithm? So it's a monovariant. There was a reason we spent some time on this with the infections. It's a great concept. Once a woman has somebody who has proposed to her, she keeps that person as a maybe. And there should be something, once all the women are matched, there is one line that we should add. Then the maybes become yes. Otherwise, we just have all the men, being maybes, and the women just keeping them like that, right? Every time we do, yes.
Does that happen before you repeat?
No, you keep repeating while a woman is unmatched, and then once all the women are matched, then all the maybes are transferred to yeses.
But they're considered matched if they say maybe.
Correct, right. So as soon as you have a match, you've got someone. Okay, so we're studying the number of matches, and I claim it's a monovariant, that every time we run through the cycle, run through the while loop, must there be at least one new match? So that's the question is, must there be at least one new match or no?
If not, I'm terminating.
Well, let's say we have m pairs. So we have n minus m men, n minus m women. So we now have the setting. We've got a couple of men and women that are already matched. Is it possible that as we go through this, that there's no matches in the next proposal?
I think it's not, because either each unmatched man will propose to an unmatched woman, so then we have more than one, or multiple will propose to, like, all of them could propose to the same woman, and she'll just choose.
Okay, so if a man proposes to an unmatched woman, we win. Right? All we need is one man to propose to one unmatched woman. Your worst case would be all the unmatched men propose to the same unmatched woman. So if at least one man proposes to an unmatched woman, we win. Is it possible that all the men propose to matched women? Could that happen? So what do you think? Is it possible that all the men really like one of the women who is already matched, and they just haven't proposed to her yet because they were proposing to other people?
No,
Why not?
they would have had to propose to her in a previous iteration.
But maybe they proposed to somebody who was already matched as well. Right? So is it possible that all the men were going after maybe the same women down in order?
Yeah, it is.
So what could happen?
Although after at least m iterations of
Ah.
then one of them will match.
So we could try to do a little bit more careful analysis right now to show that maybe there always is a unmatched woman who will be getting an offer. Or we could say, worst case scenario, imagine there wasn't. Then eventually, after a certain amount of time, all of the men would be making proposals to the same women, and the women would have a chance to upgrade. Right? And so how long could that take? Worst possibility. So this might be provable. Maybe we can prove that. For the sake of a simpler proof, we don't need to. The algorithm is of order n squared. So if we come up with something that's order n squared as well, we may have a worse constant, but still going to be roughly the same runtime. So do we think that it would take about m iterations before there will be a man who will propose to an unmatched woman? So question. Worst case, do we get a proposal to a new woman after m, or maybe it's m plus 1 iterations? Because if we look at our men, the danger is they're all proposing to people in the top. So we have m of these people. So the question is, do we have to modify our algorithm a little bit? So let's look at the algorithm. All men who are unmatched propose to the top candidate. She rejects all but the best whom she maybes. Maybe we need to modify step 1 a little bit. So step 1 is deliberately wrong. It's going to set us up in an infinite loop, potentially.
You mean to say to whom they have not already proposed?
To whom they have not already proposed, right? To the top candidate to whom they haven't proposed. It's very reasonable to add this. I'm sorry?
You said that last time.
I said that last time, but I didn't write it this time.
Okay. Well, I think we were all thinking it.
Yes, but it wasn't written on the board.
Sure.
And so in programming, what we would have happened is, imagine everybody thinks Math Bobby is the greatest, and everybody proposes to her. And then on the next round, the people who lost out, well, Math Bobby is still the greatest, so they're going to propose to her again. She rejects them again, but being good little robots, they don't really care, and they just propose again and again and again and again. And you get stuck in this loop. Anybody have any vacation messages, vacation mail programs? Anybody use these? That if you're going to be away from your computer for a long period of time, if you're traveling, a lot of people set up a vacation message so that it says, I'm away from my email, I will get back to you when I return on such and such a date. When I started college as a freshman, you actually had to physically go to a building on campus and request an email account. And one of my cousins had to convince me it was worth doing this. I know, it seems very strange. And so this is when they were just really starting having email become big. And a lot of CS majors wrote vacation mail programs. And it would be set up so that if they would go on vacation or whatever, it would send a message. And occasionally, someone would log on and send a message and then quickly log off. And this happened at multiple universities across America. Is somebody would log on and send a message to their friend who has a vacation message, who would then send it back, reply immediately, I'm on vacation. And then they would send a message back, I just got your message, I'm on vacation. And it would actually knock out servers at colleges, where it would just keep going back and forth, and it would just explode. And then, the poor people who did this would have some conversations when they got back with OIT. So how do they modify vacation mail programs now? I'm sorry? So what it will often do is it will not send it to the same email address twice within 5 minutes or something like that. Is you put in a little line like this to prevent this infinite loop. That's the danger when we don't put to whom they haven't proposed. So once we put that in, now if we come over here, now the analysis becomes a lot easier. So we have m people who are matched. Worst case scenario, you'll have like m-1 or m proposals. And then you'll exhaust everybody on that list. And then you will propose to someone new. Okay? So now the analysis isn't that bad. So worst case scenario, they all keep proposing to the same person. They keep going up among the same list here. You can actually do a much better analysis. I'm being very crude here. It's going to give the same order of magnitude, so it's fine. And so in at most, basically m steps, we would get a new proposal. So the number of steps or iterations should be basically like 1 plus 2 plus 3 plus n, which is n squared over 2. I guess, plus n over 2. Right. So this just gives you a sense of how quickly it will terminate. You can do a little bit better than this. You can do a slightly better analysis into here, but this is enough to see what's going on. Okay, any questions about this? So this is much better than n factorial. But notice that we have no freedom in terms of inputting an objective function. That's the real drawback to Gale-Shapley. You choose which side you like. And we saw last time that, at least with the example, it was better to be the people who were proposing than the people being proposed to. So an advantage of doing something like this through linear programming or through other techniques is that you have an ability to have an objective function and try to balance the competing influences. As a nice exercise, write this as a linear programming problem. Okay? All right, any questions about this? So again, almost anybody who's programmed has at some point in their life done something like this, where you get stuck in these, forever loops. The other one is putting like a semicolon after a for statement, so it doesn't actually execute the for loop, it just counts from 1 to whatever. That's another very fun mistake to make. Okay. So the next one I want to move to is the rental harmony. And so for the rental harmony paper, the idea is you have some resources that you want to distribute. And different people will evaluate the objects differently. And because of this, you actually have an opportunity to have everybody get more than their fair share of the wealth. So if you have n people and you have 1 unit, how much wealth should each person get? 1 over n. If everybody objectively evaluates everything the same way, can everybody do better than 1 over n? Why not? What's the big math phrase? Why can't everybody do better than 1 over n? I'm sorry? What would happen if everybody was better than 1 over n? It would be more than 1. This is Dirichlet's pigeonhole principle. Right? Think of it as the boxes, If everything is above the mean, the sum is going to be greater than the total. But if people evaluate things differently, you actually have the ability of everybody thinking they got a good deal. Based on the fact that my movie loves do not seem to align with yours, I've decided not to show the clip. I'll just post it from War of the Roses. Anybody see that movie? A couple is getting divorced. Danny DeVito is the lawyer. Michael Douglas is the crazy husband. And he's showing Danny DeVito his plan to divide up his house with his wife as to who gets which part of each room. And they're going to live in the house together even though they hate each other. And they've got these lines of demarcations in the different rooms. And Danny DeVito looks at him, you're crazy. He goes, no, look, I got more square feet. So he's valuing square feet very highly, but he's not valuing just a good living situation, I think, nearly enough. It's often done, you have some bar. And maybe one person has some function f of x, which says how much they value each part of it. And the other person, g of x. And so if you divide the bar into lots of different pieces, the area under f of x in your cuts will be how much this person gets. The area under the others would be how much the other person gets. And if they have very different functions, you could actually have benefits. Let's see. Anybody ever have a half moon? In New York, they're mistakenly called black and white cookies, but they're half moons. This is actually easy to draw on a blackboard. Right? There's the vanilla side and there's the chocolate side. This is an ideal situation. Some people really like the chocolate. Some people really like the vanilla. If you really like the vanilla, find someone who likes the chocolate. You could actually use this if you're playing Gale-Shapley and trying to determine whom you want to accept as your partner for life. Go for the other one. Some people like to have some of each, and they want to do the cut this way. And so the question is, how do you allocate something like this? There is a huge industry on division of assets. One of the most important places to use this, sadly, is divorce proceedings. So I figure since we've just been talking about marriage, it only makes sense to, just in case it doesn't work out, maybe you carried a 1 incorrectly or something. You talk a little bit about what happens if you have to get divorced. Okay? A lot of times we do things as very simple. Say, we're going to draw one line. And not, a bunch of different lines and just allocate among 2 people. Okay? But of course, you could do things with more cuts. Do you think it makes sense to talk about a continuous cut for resources when you're getting a divorce? I'm sorry, my TAs Cameron and Kayla couldn't be here today to talk about continuous cuts. Well, let's see, Cameron is 9, Kayla is 7, so on average our kids are 8. So one of us gets all of Kayla and the other one gets maybe Cam up to about here. You cannot divide all resources continuously. You have to make binary assignments. Someone gets this, someone gets that. What do you think would be a great tool to use for divorce? Similar to the SAC problem, linear programming, right? Linear programming, it's amazing how many things linear programming can solve. And if you don't have too many resources, if you don't have too many things to divide, some things you can divide continuously. Other things, it's 0, 1. Someone gets this, someone gets that. I know there was a divorce going on, and it was interesting because this was during the Cubs-Indians World Series, and one of the assets of the families was tickets to one of the World Series games. And they did not want that asset to be, put on hold for a couple of weeks while the judge decided who gets what, because then it becomes worthless. So, what do you do to very quickly make a decision? And I think the ruling was the father was allowed to take his son, but he had to purchase tickets for his wife of equal seating value. Well, he could have let her take the son, or he could have taken her and not gone with the son, or they could have sold the tickets. But it's who gets the right to the ticket. There are some resources that you cannot divide continuously. What incentive do you think people have in this problem? So this is getting into negotiations. And of course, I would never do anything like this in school committee business. I just want to clearly state that. So let's assume we're only going to make one cut. Okay? Do you guys remember the drowning swimmer problem? Here is some poor person who's drowning in the water. Here's the lifeguard, and the lifeguard has to choose a path. We will assume the lifeguard is not an idiot. The lifeguard knows calculus. The lifeguard swims faster than she runs. She's clearly not going to run straight like this. That's going to be the longest possible time. The lifeguard is smart enough not to be spiraling around. The lifeguard is going to run in a straight line to the shore and then swim directly to the swimmer. One possibility is to run to the point directly under the drowning swimmer, because that maximizes your time on land where you're fast. Or the other possibility is you run to some point on land. I think we talked about this when we did Do Dogs Know Calculus? It all comes down to choosing one point, right? And then we just vary that one point and then see which minimizes time. And it turns out that the answer is the same as the index of a fraction, Snell's law. So let's try to think what's going on here. We choose some point. Here is 0, here's 1, here's some point A. And so the amount the first person gets would be the integral from 0 to A of f of x dx. The amount the second person gets is A to 1 of g of x dx. What's my goal? I want to maximize those things. Well, I mean, can I maximize them at the same time? You know, as I increase, as I...
Do you have to maximize them, or do you just have to have them equal? Because like most people getting 0 is like, maybe it depends if like all you want is the other person got, or if you want as much as possible.
Now, unfortunately, in a lot of divorces, the goal is not to maximize your happiness, but to maximize the other person's unhappiness.
Right.
And you know, I'm trying to prepare you guys for real life, okay? I apologize. If you do a really good job on the Gale-Shapley, you won't have to worry about this part of the lecture. But you know, sometimes people's objective is not to maximize their happiness. They're getting their happiness from maximizing your unhappiness. What if we got these two to be equal? Does that seem fair? You know, we have to decide how we're dividing this. You know, you've been hired as consultants. All you have to do is just tell me a value of A. That's it. And we're going to pay you a huge amount of money. So I want you to give me proposals. One proposal is choose A so that equal. Do people feel that this is a possible solution? That this is something that you can say, you know, this may not be the best solution, but this is something where you can make a good case that this is reasonable, this is fair. Each person ends up with the same amount. Is such an A possible? Does such an A exist? It's not necessarily 1/2. How do we know such an A exists? So let's let R of A equal the integral from 0 to A of f of x dx minus the integral from A to 1 of g of x dx. Okay? Comment or? I'm not making comments. All right. We have the resource difference. Okay? How do you prove that there is such an A that this equals 0? You could use the mean value theorem, but I think I would use a theorem other than mean value. I'd use intermediate value theorem. So what is R of 0? So what would R of 0 be?
Minus integral from 0 to 1 gx.
Right, and so it would be -1. You know, because in this person's mind, they have everything. What would R of 1 be? 1. Therefore, intermediate value theorem implies there exists an A such that R of A equals 0. And in fact, what we can do is we just keep increasing A until they're equal. So we have a nice way to flow and get the answer. So do we agree that this is a possibility? What's the danger with this?
Should we just keep increasing A, or should we do a binary search?
I mean, we could do binary search. There's lots of different ways to find it. So yeah, I mean, I would probably try a half and see what goes on there. And if it is, you know, positive, then what we would do is we would decrease A a little bit and go maybe to 1/4 and hop like that. So yeah, I mean, a binary divide and conquer would be a good way to find A. Is there a problem with this method? Yes.
What if people end up unhappy?
Why would they be unhappy? Well, I mean, why would they be unhappy? They have the same as the other person.
Because like if f of x values it less, they would have to end up with the A being higher in order to have the same.
So here's an interesting question. Could you end up in a situation where each person has less than 1/2? According to their own valuation. So here's 0, here's 1, maybe here's the point 3/4. So maybe, yes, maybe the first person assigns a value of 1/4 through here, and then 3/4 over here. And the second person assigns a value of 1/4 into here, and 3/4 into here.
We don't have a constraint about must sum to 1 or anything like that.
So we don't have a constraint that it must sum to 1.
Or like that it must be maximized. All we're saying is equal.
But now, if we try to extend this further, well, this person's happiness would increase, but this person's...
We're also like not approaching it from both sides, if that matters.
Well, right, but I'm saying if we increase this over here, this person now has more than 1/4, this person would have less. So if we had this assignment, are we going to be able to do anything better than each one gets 1/4? No. No, if we could only make one cut, this is the best we can do. Right? So one problem with this formulation is that it does give us a situation where we could end up with somebody having less than half, and the other person has less than a half. And so both people feel they got a bad deal.
But we couldn't flip it the other way.
I'm sorry?
We couldn't give them the opposite portion.
Well, no, that's interesting. In this case, if we had actually done it the other way,
Can we define it as RA as like the max of integral 0 to a f x dx minus whatever we have, and then I'll take that and integral 0 to a g of x dx minus a to 1 f of x.
I'm going to try to reinterpret what you said faster.
Sure.
Basically, I think this is what was just mentioned a moment ago of flipping.
Right.
If
But can we like do it as an actual
Yeah.
function?
Yeah, and so what we could do, I would then say, once we get this A, we look at the maximum of the two possibilities. Because we know if these two are equal, then these two have to be equal. Right? And so since these two are equal, those two have to be equal because they all add up to 1. So what we could do is we could say we choose our point A. How many choices for A will there be? Is A unique or not unique? So is A unique or not unique?
Doesn't it depend on the function?
So what can you say about these functions? Let's assume we assign value to everything, so that if you get something more, you give it some value. You give me an Alex Rodriguez, jersey, I'm not going to assign much value to it. I would have even trouble selling it. You give me a Jar Jar Binks doll, again, I'm not going to be that thrilled. Although we did destroy a Jar Jar Binks doll years ago at Williams. I still have some of the pieces. But let's assume no matter what you get, you are increasing your value. You could have a function g that's flat, that says, I'm not going to assign any value to things in through here. And if f also assigns nothing in there, you could have a whole range. Or you could have, okay? So we'll assume that, let's assume that you always assign value. So we will assume that f and g are strictly greater than 0. So you are always assigning some value. Will A be unique now? So under this assumption, will A be unique? Yes. So now there exists a unique A. So exclamation point after there exists means unique. And then by looking at the cut and the flip, look at cut and flip, ensure each gets at least 1/2 in their mind. So do you agree that this will allow us so that when we have our divorce and we're splitting the rod, in each person's mind, they feel that they got at least half the value? This is a wonderful result. right? It seems fair. Each person is getting at least half the value in their mind, so nobody feels like they're being screwed. And if you look at it from the other person's perspective, they feel that they're getting exactly the same value as you. So, well, okay, maybe I'm getting 3/4, but so are you. Or maybe I'm upset because you're getting 4/5, but in my mind, I'm also getting 4/5. So do we like this way to divide things? Again, I hope you never have to use this, but do we like this? So how many of you have ever heard of the phrase gaming the system? It's interesting to see whose hands go up really fast. How could you game the system here? What's the danger? I'm sorry?
Like false value, undervaluation.
Deliberate undervaluation. What if you are the G-man and you really like the stuff down here? Value it low. Right? If you value it very lowly, then you're going to get a lot more than you should. So the question is, when you're doing something like this, do you actually have an honest evaluation of someone's F and G? And so when we're doing problems like this, when we're doing division problems like this, this is assuming an honest appraisal of the two parties of F and G. Do you expect an honest appraisal of the two parties? If you don't want to think of divorce, think about negotiations between businesses when they're trying to decide what kind of office to make. Do you think people publicly say what things are actually worth to them, or do you think they try to get a negotiation advantage? So one of the dangers of this method is that it is open to people lying about their correct values. So for the next class on Friday, what we'll do is we're going to continue this problem, and we're going to really delve into the rental paper. There's a lot of stuff there. I'm going to concentrate just on the part of dividing, I think, the rent for rooms among 3 roommates. And it's a really nice application of Sperner's lemma. You have to first do a nice triangulation, and then from that triangulation, then you do a twist, and then you get to Sperner. Okay.